ऐसा ऐसा इसे मैंने कल ही कह दिया था, मैंने कब कल छुट्टी मत देगी, नहीं छुट्टी मार जाता है। छुट्टी पे चल रहा महीने भर नहीं, आज तो आ गया, कल कह रहा छुट्टी मार जाऊंगा, मैंने कहा काम जब भी होता है जब भी छुट्टी मार जाता है। काम जब हो और जब बच्चे गए तो चला दो, लाइव चला उठ गया। जोड़ दो बस, कोई ना।
Chica Mike. Chica.
ये कौन
Start.
Students, please maintain the decorum. Welcome back everyone. We now move towards one of the most awaited session of today's conference. It's my privilege to invite our esteemed speaker, Professor Dr. Anurag Sharma Sir, IIT Delhi, to deliver the expert talk. Please welcome him with a huge round of applause.
हेलो
Good afternoon. Welcome back. Good afternoon.
Not
Good morning. Okay, good morning. Uh, Welcome back to the session.
Yeah.
Charlie.
Okay. Yeah. Yeah. Continue. Okay. So welcome to this technical session now. As you can see, I'm going to talk about optical fibers. Optical fibers, as we say, are ubiquitous and everywhere. Uh, communicate with the Wi-Fi, laptop, there are many other groups where some of those things and then also talk about here and there. Then also so not very far from here, there is something called so in 1948, a young graduate from a college joined the Organs factory in Rajasthan as part of the business labs. Had a Organs factory. In 1950, went to Meerut college. He left college. Did his optics and his PhD. He finished his PhD on transmission of fibers. Yeah. Hello.
मयंक है
Can you hear now?
इसको
Yeah. So subsequently he moved to US and became one of the private. His name is Narendra Singh Kapani. Kapani, I'm sure many of you have heard his name. He in 1950 when he joined Hopkins, he made first fiber scope, which is basically using fibers. You would make an endoscope, go through your body, and you see what is happening inside. And today, most or all actually endoscopes are based on fibers, so then they can be flexible. Before that was a rod, it was not flexible and okay. He also invented the coated glass fiber. I'll show you the structure. Glass fiber is a hair thin glass rod which is also coated with another glass, and we'll see why it is done like that. He invented that technology. He also gave the name fiber optics, which is now used all over the world. He wrote the first book on fiber optics ever in the world in 1967, and he is actually called father of fiber optics from that point of view. When he died, he was back in 21. This is the New York Times headline which states that the father of fiber optics dies at 90. And this is the double crucible technology which he developed for the coated glass. So you have one glass, molten glass here, the other one here. This tube for some time and the cladding comes and then solidify, and that is how the fiber is made up. But today's technology is very different. So why this fiber is like that? What is it? what is happening in this. We all know that, I'm sure you have done fraction of glass of light by media. So when you go inside from rarer to denser media, the light towards the normal. When you go the other way around, light goes away from the normal. And if you keep on increasing the angle in the denser medium, the light will actually, the angle will go on increasing and ultimately become 90. And then we have the critical angle. And after that you have total internal reflection. Have you heard of this?
Yes, sir.
Good. So if you have a medium which is higher index surrounded by lower index, and if you launch light inside that, then because of total reflection, most of the light will remain inside. That is what happens in a water jet like this. You have a water coming out, surrounding is air, so light. So this is how the light will guide and it follow the paths of the dark region. Not that strong index. This was demonstrated in 1842 by Madden. And this kind of technology was then used to make these colorful mountains all over the Europe at that time. And today, of course, you can see all over India also. But this is because of most of the light is going through, but some light is coming out. That is how it is. You see the lighted paths, right? Because of the curvature, some light comes out. But if it is perfectly straight, then the light will not. So this is the structure of an optic fiber. You have a core which is of higher refractive index, then surrounded by a cladding, which is again a glass, which is of slightly lower index. The difference could be so small. And beyond that is of course polymer jacket, because glass is fragile. As you protect by polymer jacket, it can break and it can crack. So this is the structure of the fiber. I'm sure, have you seen? Most of you have seen?
Yes, sir.
Good. So, so if you just look at the fiber, you don't see this structure. It's very, very small, because typically in a single mode fiber, this is about 10 to 10 micron or so. This is very sensitive. I did not even touch. And this outer diameter is 125 micron. So, 8 one by one on the side on the table. It's extremely small, very thin. But with polymer jacket, it becomes a little thick. So we say light confinement is like total internal. So the optical fiber is a long, narrow, cylindrical component made of silica. Silica is the basic component of glass. And since we want to make the core slightly higher index, so we dope the silica with germanium. So the refractive index becomes larger, slightly larger. We want very small large. We don't want very large. And the cladding is pure silica. That is how it's made. All the other materials are used for different wavelengths and so on. Glass has the property, glass is a frozen liquid, you can shape it the way you like, and that is how you have all the crockery and decorative things. It melts very easily, and then you can shape it and becomes hard. And that is how fiber is made. We'll see how it's made, and because of this flowing property, it keeps the structure that is. And we are trying to make this fiber, this structure which is cladding and core and so on, for kilometers now. Typical fibers, one fiber which is made in the factory is about 10 kilometers. So you can imagine the aspect ratio. You have 1/8 of a millimeter like this and 10 kilometers. That is and it has to remain almost uniform and so on. That technology. These refractive index can be modified by doping and so on, and dispersion and so on. Highly transparent in the visible region. That is how you have It's very transparent till about here infrared. Due to this property, it's used extensively in optical, which is all optical devices. So in glass fibers that were used in endoscopes, endoscope is only half a meter. But when you want to use this for communication, you need kilometers. So that makes a difference. So anyway, the endoscopes were made by optics. Although the first endoscope was made by a German student, but later on, optics did a lot of work on this, and it became famous. And today, all are made of. I don't know whether any of them. So optical fibers, the real application is in communication. So the in 50s it was established as endoscope. It was only in 1960s when the lasers came. After that, people started thinking about using optical signals, communication, and then fiber became important, but not. But it was not easy. As I said in the morning, logical thinking and all those things are on into this rejection and acceptance and so on. We'll see that. So let's look at what is communication. So communication, the first actual communication, electrical communication started with Morse, with telegram. Not the telegram that you kids use. The telegram was a communication device. Telegraphy it was called. So you could send dots and dashes and so on with in symbols and on. So they were assumed, agreed symbols. So you send something that's the other side they reach and then one sentence and one word and those kind of things used to be. Older age group will probably have used it, but today it is officially dead all over the world. Nobody uses Telegram because Telegram is now used by something else. This word is used by something else. So Telegram is completely gone. So that technology, that shows, how the technology survives. From here to here, from here to here, how many years? 40 years. So Bell telephone came later on, and another 25 years. By that time, between Bell and so on, the Maxwell had come. I don't know whether you heard this name Maxwell. Anybody? Have you heard of the name Maxwell? Yes. So Maxwell is the one whose equations we keep solving. And in fact, the entire electromagnetic theory, entire optics, entire radio waves, entire everything is actually just those four equations with Maxwell. And that is the basis of all further developments. So the radio waves, which were also got by J.C. Bose before Marconi, but J.C. Bose being a scientist, true scientist, he didn't patent anything, he didn't do anything, but Marconi did, and he made a company and so on. So that is how the radio waves started. And in 1940s, microwaves came. And see, if you go from radio waves to microwaves, what has changed? Both are electromagnetic waves. The frequency has changed. Radio waves, the frequency is about, what is the frequency of radio waves? FM radio? What is the frequency? 106 megahertz. 106 megahertz, right? So it's typically 100 megahertz and so on. Whereas microwaves are gigahertz. 10 gigahertz, 100 gigahertz. So there's a change of about 1000 or 100 or so. And it is known, it was established that as you increase the frequency, you can send more signal. It's like a template. Frequency is nothing but like a template. I mean, if you have a graph sheet which is millimeter graph, you can code more things in that. You can make a finer picture as compared to if it is a centimeter graph and things like that, right? So higher frequency means better template and you can send more information per second. So people wanted to go higher and higher frequencies. So that is why radio wave to microwaves during World War II, and microwave became a very, very important thing, and then it continued. But people wanted to use light, because light is another 100,000, 1 lakh times zyada frequency. Gigahertz is 10 to the 9, light is 10 to the 40. So 100,000 is a huge number. It's a huge number, and people were always wanted to use communication engineers wanted to use optics or optical waves for communication. But the problem was there were no strong sources available. You need to send light kilometers distance, right? So if you know that when you go in a train, if it's a village very far, you hardly see the light. The light sort of scatters in air, and also the light has a problem if there's a fog or rain, the light will be lost and things like that. So there are a lot of problems with light. So two things were required. One is source, the other was a medium, how to take light from one place to another place without being disturbed. The source came in the form of laser in 1960. Right? Lasers were invented in 1960. Which date? Date? 1960 is the year. I'm talking about date. So it is 16th June 1960. Right? So 16th June is now not 16 May, sorry, 16th May 1960. 16th May is now celebrated as the International Day of Light. Okay, it's the International Day of Light every year. So lasers came. So lasers are very strong directed source in one direction. They can send very high amount of energy, high amount of brightness, and so on. But then the problem was still how to send, because you send laser from one place to another place, and suppose it rains in between, the laser is lost because of strong scattering. Because as the frequency goes up, the wavelength goes down because velocity is constant. And when you have microwaves, the wavelength is in centimeters, so the small things doesn't bother centimeter wavelength. But when it is light is 1 micron, then even a small particle will scatter it. So that is the problem. So you needed. So optical communication became a possibility due to laser. But then a guiding medium was needed because of the reasons I am saying. Because you needed a secure, not only secure, but safe, without scattering and so on. That kind of thing. So optical fibers were around at that time. Because optical fiber technology was developed in 50s by, and then this is 1960s, so it was mature at that time. So the optical fibers were immediately taken for this purpose, and they were summarily rejected. But they are not useful. Why? Because the loss was very high. This is where the length comes from. So endoscope is only half a meter. So if you put 1 milliwatt light on the side, the other side 1.99 milliwatt. But if it is a kilometers long, you send 1 milliwatt, hardly anything comes out. Because the losses were about 100 dBs per kilometer. 100 dB means it comes, if you have 1 going in, 10 to the minus 10 will come out. There will be nothing left. So that was the problem. So this is the typical glass loss in technology, glass technology development. So it is here, it was about 100 dB at that time. But microwave communication, the target was, so they had 20 dB of kilometer. So the target for optical communication was 50. They had to have 20 fiber communication channel, which is 20 dB. So you have to have a technology. So the communication rejected optical fibers as a medium, and they started trying many other things. Which today, if I read those papers, I've read those papers when I was in PhD. If I read today, there's something here, kind of things, steel pipes, polished pipes, all kind of things, gas lenses, a variety of things. Fortunately, fibers rebounded and came back. So it is this guy in 1965 did a research. He was not convinced about the loss in optical fibers. He said, let me see why this loss is there. So he collected fiber samples. Tell me. लेजर तो आएगी नहीं, स्क्रीन पे लेजर नहीं आती है। It's okay. ये इस पे नहीं आता है, Okay, so he collected samples from various manufacturing companies and analyzed all those. So was his PhD student. It was his PhD, entire PhD was on that why there is so much loss, and they figured out the loss in glass was because of the impurities in glass. If you take a pure silica, the loss is much less. So he prescribed that if you make a pure silica, use pure silica, you can make a fiber, and he also gave a full design, what should be diameter, what core cladding, etc. etc. So full given, and he was given Nobel Prize for just one single paper. He wrote only one paper of that kind, and that Nobel Prize was given because this rebounded optical fibers. And the team from Corning Glass Company, they got convinced with his argument, and they said, let us try to make fibers which are of pure silica so that the losses are less. And they developed a technology called chemical deposition technology, where they started. You see, earlier what was happening, people were starting with, they would buy glass from Corning or from Short and so on, and then drop fibers. So the losses, what were there in the glass, were already in it. And since glass was mostly used for lenses and things like that, which are very thin, maximum glass thickness would be centimeters. So they didn't bother so much about this loss. But here, thing was totally different. So what they did, they started not from glass, but they started with the original material, chemicals and oxygen and so on, which could be purified to a very great extent, and then made a fiber from here, and that fiber had 17 dB. So the 20 dB barrier was reached, and that was in 1970. In 1970, the other thing that happened was the room temperature laser. Double heterojunction lasers were developed. That also got Nobel Prize, that particular technology, and the lasers at room temperature. These two things completely changed the scenario for communication. And by 1965 or 1975, the fibers with diode lasers were already being used for communication purposes in the United States and Japan. They've already laid fibers for this particular. And since then, so the loss which was stuck here at 100 came down like this. And today, the fibers have lost. Okay, so this is the fiber structure again. The core, it can be anything between 10 to 50, and outer diameter is 125, and that is how the light goes through. And this is a step index fiber. Step change of the refractability, right? This is so optical fiber waveguides were studied from 1961. The first paper, now I'm talking about little theory here, how the understanding of now the understanding. So Snitzer in 1961 made the first study on the modes of the fiber. What is a mode? You have seen string. In the string you have fundamental mode, higher mode, and so on. So any resonating system, resonating means something comes back, comes back, is a resonance. Whenever a resonating system, then only certain frequencies of certain solutions will survive. Here also what is happening is, you have light going up and down in the transverse direction. So like this, in the longitudinal direction is going up, but in the transverse direction is going up and down. So it becomes a resonator. And that has only certain solutions of maximum frequency allowed, depending on what the wavelength is, depending on what the refractive index is, what is the size, and so on. Those solutions are called modes. That's a very important concept. So Snitzer derived these modes for the first time and showed that these are hybrid modes. They are called EH and HE modes. Let's not worry about that at the moment. Later on, 1969, a mathematician, A.W. Snyder of Australian National University, simplified these modes. They were very complicated because they are all vectorial and so on. But the refractive index difference between core and cladding is so small that actually you can make an approximation. And that approximation was made by Snyder to make the asymptotic solutions, which were later refined by the Cloquet to make what is known as linearly polarized mode. You have HE mode or LP mode. So you work normally with LP modes, linearly polarized modes, simple modes. Right? So fibers which are used in communication are by design a very small difference between core and clarity. This is a refractive index. So like third decibel plays the difference between, right? This is for the reason so that you can send more information. So this is very ironic. We want the difference, but we don't want the difference too much. We want very small difference. Because higher the difference, lesser is the information that you can send. So that is why small difference is kept, and that is fortunate for us because then we can use this approximation very well and model all the properties. So this is the if you look at the Maxwell equation, this is the vector wave equation we get. But if n delta n, that means change of in front of this term is less, then this term is dropped, and you got a very simple thing, and that is how they linearly prove. I'll not go into the detail of this. Say is this. So the fiber can support either guided modes or the radiation modes. Have you done quantum mechanics? Anywhere? No? You understand quantum well? If you understand quantum well, then in quantum well you have discrete states and then you have continuum. This is exactly the same. You have certain. So if the TIR is happy, then inside, along with TIR, also you have to apply the resonance condition. So you have only discrete modes inside. That means the angles which are allowed are only not continuous. But if it is TIR is not happening, refraction is happening, then the light is going out. That is called radiation. This is how roughly. So you have this. If you look at the spectrum, you have guided modes, radiation, and usually when you excite the fiber from a laser, let's say, inside you excite both radiation and guided modes. After some time, radiation modes are lost. They have gone to they are absorbed by the cladding jacket and so on. What remains inside is only the guided. Guided modes are the one which will carry energy to the other end, 6 kilometers. The main study is guided. You don't worry about it. It only used to calculate how much is the loss of the coupling. 1 milliwatt of power inside, how much power goes into the radiation, but rest is all. That is what. That's not. So in optical fiber theory, this is a very important number. It's called B number. It contains the refractive index difference, the current clarity, the diameter, the radius, and the wavelength. All the important properties have is just one number. And this number decides how many guided modes it actually contains. For a step-index fiber is less than 2.4048, then have a what is known as single mode fiber. That means in that fiber is one mode problem. What is the advantage of one mode? Then there is no more mode interference and there is no other things. Very stable power remains inside. Very stable power. This is the structure. This is the LP01 mode, which is the fundamental single mode fiber. This guy. And these are the fields. This is the intensity. So this is the meaning of the. Only these exist inside the. There is no other field pattern that will exist because of this resonance condition. I'll not go into this detail because I'll just come here. So now inside this fiber, you see, if you send light, then light can go direct like this also. It can go like this. It can go at different angles. Let's say this is the critical angle. Then anything in between is possible if it is a highly multi. But if it is mode fiber, then only discrete angles are possible because of the discreteness that I've guided. Each ray corresponds to a. But let's worry about right now. Let's say continuously. So this, if I add the input and I send a pulse, very short pulse like this. That means the intensity only at one time. Then it will excite all these rays. Now this ray will come very fast. This ray is slowest, and all other rays will be in between. That means when they come on the output side, what was an impulse will become a broad pulse. It will become a broad pulse. The fastest will arrive at this time and the slowest will arrive at this time, then become broad. What was a very small pulse become broad pulse. Now what is the problem? When you are sending signal, when you speak something, it's digitized, and you are actually sending zeros and ones. Zeros and ones means pulse or no pulse. So how many pulses can you send per second will depend on how much broadening that takes place at the end. Otherwise, they will start overlapping, and you will not be able to distinguish whether it is a zero or a one or two ones or one and things like that. So you have to have slot of each pulse. The slot is decided by how much is the broadening, and this broadening depends on the difference between this fastest and the slowest, and the slowest is because of this angle. And if the angle is not very large from zero, then the difference is less. That means the critical angle theta c should be large. Only then this complementary angle theta would be small. That means the n1 and n2 difference should be small. And that is why we keep this n1 and n2 difference small, so that this becomes this width is proportional to n1 minus n2. That is why we have fibers with very small difference, smallest possible. And that is how there's one way, another way of compensating this is that if I here the refractive index same everywhere, if I make the refractive index graded as we say, it is high here and low here as you go on, it is gradually decreases, then what happens? The ray which is going at a high angle will reach in the region of the lower refractive index. And lower refractive index means higher speed. So the ray which is taking a longer path is actually traveling faster. So they will compensate. The length and the speed compensate, and they reach almost at the same time. The broadening becomes less. This is the beauty of fiber design. And this, in the 70s and 80s, this was a big game. How to design fibers. But these are multi-mode fibers. There are thousands of modes in this. But soon it was realized that single mode fiber is the one, because there's only one fiber. Then there's no various paths, there's only one path. Okay? The dispersion or let's say broadening becomes much less. And so on. I mean, I'll not go this. So these are the communication systems which were developed over the years. In 1965, first glass fiber was proposed by Cow. 1970, first low loss fiber was made, as I talked about. 1970 to mid 70s to late 70s, the first generation optical fibers were used, which were actually gradient index multimode fibers because of this dispersion property. LEDs were used as sources. The silicon pin diode was used as detector. Wavelength used this had 45 megahertz as the data SIM, and the repeater spacing was 12 kilometers. Second generation was the system goes to 1300. Why 1300? Because the 1300 material dispersion itself is very small. You know, the glass itself has a material dispersion. That means by itself it has sort of broadening. That is less, so it was shifted here. And once again, you had 45, the repeater spacing was increased. Later on, single mode fibers started. Single mode fibers, which only one mode could propagate at 1300. The data rate became several hundred megahertz. Input spacing went to 40 to 50 kilometers. And now we have fourth generation, which is more or less today. This is working at 1550. Because at 1550 the loss is very small. At 1300 the loss was about 0.5 dB per kilometer, and at 1550 is 0.25. That means you can go twice the distance for the same loss, right? So that was a big achievement. So the entire communication shifted. So today we have repeater spacing more than 200 kilometers, data rates of 1 gigahertz or more. In 90s we used dispersion pattern fiber, which actually use multiple wavelengths. Division multiplexing was used. That means in one fiber you are actually sending 100 wavelengths, and each wavelength was one channel separately, and they could all simultaneously go through. And then we have several tens or thousands of gigahertz. There are hertz that each, and the loss was compensated by amplifiers. We'll talk about that if there's time. So there's loss is not a game right now because you can actually amplify in between. So today you can actually have a fiber of thousands of kilometers going without anything in between. So that is why the biggest communication system, the best communication system in the world is always from New York to London, undersea cable. That is called transatlantic telecommunication cable, TAT. So TAT 1, 2, 3, 4, probably 15 is running now. So whatever the best is for that. But technology is developed for that. So that's the maximum communication. And that is the one. And if you have to have a repeater or something in between, that means bring the fiber cable above and so on. But now there's nothing, just fiber goes from there to there, everything happens inside. And there's no station required mid-sea. Let's not wait. This. The single port fibers in the mid 80s became a big game. So that is how this. Initially, they were not. The diameter was very small, but we joined them. All that technology developed in mid 80s, and single port fiber became the fibers. And then a lot of studies were made how to study how to model their propagation, how to do this thing. And we had also contributed something there in 1982, where we looked at how we can approximate this very complicated fiber. Then there were also side polished fibers made to make sensors and so on. Then came in the late 80s another kind of fibers in which the cladding was actually is a maze of folds. This is called microstructure. So what happened? The idea was that you have core of silica and this of air and silica combination. Air silica combination means the refractiveness will become naturally low. So this was all pure silica, because when you dope with germania, the loss becomes higher. So just to overcome that, people thought we make all silica fiber. So that is what was made here. But this was not very successful from that point of view, but it actually gave rise to many other things. This is a microstructure fiber. Other kind of fiber was you have hole inside. So here the guidance is not because of total reflection, because inside core is air and outside is higher refractiveness. PIR cannot take place. So here it was because of photonic band gap. So these were periodic structures. And in periodic structures, certain bands were allowed and certain bands were forbidden. So if you put the light into this hole in the forbidden band, then it cannot escape because it cannot propagate in this. It remains. This was called PBG guiding or photonic band gap guiding. These fibers, these are hollow core fibers. I'll come to this. These are various microstructured and how some studies on this. There's some papers on this. A recent development, I mean, this I've already talked about WDM, up to 100 wavelengths can be sent. Polarization and angular momentum can be used for sort of multiplex these days. This is being studied these days. Because, you see, the point is, in spite of all these big data rates, the demand is even more now. Even today, you want when you press your button, the entire movie should download within seconds. It doesn't happen still. And there are a lot of delays. So that has to be, so there's a lot of research still going on to increase the capacity. And these are some of the things, more division multiplexing and fiber designs, all these things are happening today. Let me just maybe that. These are new kind of designs where you have multiple cores and various designs. Not these are also some new designs. This is I will talk about. There are other complicated designs also. So now today hollow core fibers are being these kind. Why? There's no material loss because most of the light is here in air, so there's no hardly any loss. No material dispersion, no nonlinearity because if you have high intensity, there's a nonlinear problem in glass fiber, and no reduced speed. This is very important. See, when you have glass fiber, the refractive index average is 1.5. That means your velocity is c by 1.5. But if it is air, then the velocity is about c. Right? So the delay, this is called two-time delay. This has become an important issue in data centers and all those calculations because we want any delay of that kind is also in nanoseconds and so on, which is a problem. So this is also very important, and so much so that this has become such a big game that Microsoft has bought a full company, which made very special kind of fibers, hollow core, to have fibers for their data centers. They have now bought a company with talking about this particular thing, right? But this is 47% more, that 1.5 versus 1. That is more, speed is higher. It's not data speed, it is the actual speed, signal speed. This is very. So these are the kind of things, and then these are the same thing can be done in BRAC fibers, where you have a hole here, but these layers are now radial layers of alternating refractive index. So once again, you have a band gap here, and you can actually do. These are called hollow fibers, BRAC fibers here, and this was by Jay in 1970. Then experimental realization came much later. In this is what happens. So these are the layers. So this is a lower refractive index. Light is confined because of periodic layers. Okay, so K is like this. It does not, loss is not zero, but it's very, very small. Another device which is very, very useful is a fiber BRAC grating. So inside the fiber core, you make periodic in the length direction, you make periodic structure. That becomes a BRAC reflector. BRAC reflector means actually what is happening is from each layer there is a reflection, but if all these reflections interfere constructively, then there is a huge reflection. And this will happen if the period is roughly lambda by 2. But lambda by 2, then this comes back, it's in lambda. It's also lambda. So all of them are in phase, and the huge reflection. And this is the BRAC grating. This is how the spectrum of this comes. The reflectivity is very high at a particular point. The wavelength and rest is very small. This is used extensively for as a reflector in lasers, for example, laser reflectors. It is used in sensors and many other places. So BRAC is a very strongly spectral device which is used. This is all inside fiber, which is 10 microns. This entire structure is being written. So the technology has been developed, the theory has been developed, and these are sensitivities. So the BRAC, one of the biggest applications of BRAC gratings is that you have a fiber, you have gratings of different wavelengths. That means this is like lambda 1, lambda 3. And if you bury this inside, let us say, a building and so on, if there is stress here, moisture deposit or anything, it will send a signal. So these are called distributed sensing. It is not only sense, but what is, something is wrong, it will also tell you where it is. That is the advantage. And this is what these kind of sensors are being used for. So optical fibers as sensors, I think Satyendra is going to talk about. I don't know what he's going to talk about, but he did PhD in this. The next speaker, he did PhD in IDD, these kind of sensors. So it's a very simple technology. That if you remove some part of the cladding, then the field comes out, and if you change the refractive index that place, the intensity which is going through the fiber will change. This is a mechanism of sensing. You can sense refractive index, you can sense temperature, you can sense pressure, and so on. These are the optical fiber sensor is a big technology. And so they work on surface plasmon resonance. That means instead of you remove the cladding and deposit some metal there, and then metal has a surface plasmons. They interact and that becomes a very good sensor. This is how it is. You have metal layer, the light going through, and it will have a resonance. It will have wavelength dip at a point, and this dip will change as the refractive index changes. Changes. So by measuring where the maximum is, looking at the spectrum, you can actually figure out what is the refractive index that is surrounding. And once you know the refractive index changes the temperature, so you can actually convert it to a temperature sensor, pressure sensor, and so on. That is how. Another device which is used is a photonic lantern device. Photonic lantern because structure is something like this. So here the device, you have a multi-mode fiber. You have a device, single mode fiber. And then again, what is the advantage? In single mode fibers, you can do fiber bracketing. Multi-mode fibers, you can't do that. When you do fiber bracketing, that means you actually suppress some part of the spectrum. Some wavelength can. So the light which is coming through this, you can actually modify the spectrum of that and get it. So this device was made for astronomy. So in astronomy, what they do is the signal is coming from the stars. They collect at the telescope and is transported through optical fibers. That is today it is being done. In these stars, when they come through the atmosphere. The light which is coming from the star, and the atmosphere has its own molecules which modify the spectrum. So they wanted to suppress that part of the spectrum, which is very, very narrow, to get the actual pure spectrum of the star. And for that purpose, they wanted to suppress certain wavelengths. And for that, they approached some of the people working in optics labs, and they proposed this device. And this has become now a big device because this is also a device which is used for space division multiplexing. So you have several single mode fibers, each one have a single communication line. Find them, this is multi-mode. So different modes correspond to different here, and you can have single fiber several modes going, which each carry a different signal. And then that is what is known as space division. The core of this lantern is the adiabatic transition. Adiabatic transition is a quantum mechanical concept. That means you change the system, but the mode remains the same at every stage. And that is how that's shown here, but that's not. So this is what happens in a photonic lantern. So you have, for example, you have 6 single mode fibers which are going, ultimately will to one multi-mode fiber which is 6 moded. Then what happens if you excite this fiber? This will go to LP11 mode of the multi-mode fiber. Excite this fiber to different mode. Excite this fiber. So there is a one-to-one correspondence. So that means 6 channels can be all fitted into one fiber of 6 modes. And that can carry light, and the other side to the reverse of this and separate them out. So this is known as space division multiplexing or mode. This is to increase the capacity. The other thing that has happened is, and this is again, in optical fibers, the light is confined to 10 microns. So if you have very high intensity, let's say 1 watt you said, so it becomes 1 watt per micron or 10 micron square. The intensity becomes very high. And the linear optics entirely depends on intensity, not the whole. So inside the fiber, you can do a lot of non-linear optics. Okay? And one of the biggest applications of that is the supercontinuum of light. What happens is, if you send a pulse, very strong pulse at, let's say 800 wavelength, as it propagates through fiber, it becomes such a broad spectrum. it becomes about 2 kilometers only. So there's about 30 interaction between them. And this is entire white light. This is known as super continuum. This white light is not like this white light which is incoherent. This is a coherent white light. Wavelengths are, all of them are coming from the same. This is a very special property. This kind of source was possible only because of this optical fiber, where the core, in fact, 10 micron is also very large. So actually, people use this kind of fiber, but this is actually 1 or 2 micron only. Actual core is only 1 or 2 micron. Very, very small. Very high intensity is generated, and you have the supercontinuum light. Finally, people have also made what are known as optical fiber amplifier. What inside the fiber, if you dope with erbium, then it becomes an amplifier. Okay, and so you pump that particular thing, and then the signal which is coming in the fiber will simply amplify. And that is why today we don't worry about loss. So you can put amplifiers, and these amplifiers are such that all wavelengths in WDM are simultaneously amplified. All pulses, data rates, everything is amplified. So just you have a communication in between an amplifier fiber, which is formed from outside with another laser, and that is our DAT. This kind of thing is a boon for us. Then the same thing, if you take an amplifier and put two mirrors, becomes a laser. So fiber laser is another technology which has become a big thing today. All car manufacturing, fibers are used for manufacturing a lot of things. This mobile phone, car manufacturing, cutting, everything is by lasers. Those are all now fiber lasers. And in fact, for defense purpose, now you have seen a lot of wars are going. Lasers are being used for target locations. Most of these are now fiber. Because other lasers, they are very flexible and very light lasers as compared to other lasers that were used. So these are the kind of things which are being used. There are some of the this kind of manufacturing. This is a small head and can be computer controlled very easily moved. And so all these are used. This is the pictorial representation of what is happening. This is the actual picture of target. This is how the lasers. Everything, all sources, everything is at the end. There is a long fiber and the laser comes out. It's a very light head and it can be very easily moved around and kill. Okay. So this is all I wanted to say. So we have, this is we had cladded fiber development, then low loss fibers, then gain index fibers. Then the operating wavelength changed from 820 to 1300 to 1550 for communication, taking advantage of loss and dispersion. Entire engineering was done. Dispersion shifted fibers came with dispersion, and so on WDM, EDFA, all these developments that I've talked about. Then today hollow core fibers are the technology. Today microfibers is part of this. The space division multiplexing is being used. Photonic lanterns are one of the devices for that purpose. Only devices, sensors, amplifiers, and lasers are all inside this fiber, which is 10 micron. So this is a wonder element that we have. Fiber bracketings have changed completely the sensor market of sensor technology, and bracket fibers in that are also for sensors. Anyway. There are like a time so not have you have a band structure, that means certain wavelengths of light will propagate, certain wavelengths will not propagate. So we concentrate on the ones which will not propagate. Then we create a defect. That means we create in the center somewhere a defect. Either the hole is filled or it is a bigger hole or whatever. And then we put that particular wavelength light which cannot propagate here into that. Then it cannot escape. Then it sort of remains confined. That is the technology.
Thank you so much, sir, for sharing your invaluable knowledge and insightful perspectives. Your words have truly inspired us. Once again, please give a huge round of applause. As a token of our deep respect and heartfelt gratitude, may I now respect our respected director, sir, to kindly present a memento. Our convener and co-convener and Principal Pharmacy, Dr. Neeraj Kant Sharma, sir, to kindly present a memento to our esteemed chief guest, Professor Dr. Anurag Sharma, sir, in recognition of his distinguished presence and invaluable contributions to this prestigious conference. May we have a huge round of applause. Thank you so much, sir, for your valuable time. We shall now commence the poster presentation session of ICRIST 2026. The session will be held at the Auditorium Corridor B Block. The session will be chaired by Dr. Sapna Deshwal, ma'am, Head of Department BSc Chemistry. The session will be coordinated by Dr. Suman Gupta, ma'am. May I request all the poster presenters, delegates, and participants to kindly proceed to the venue and be ready with their presentations.
सचिन सर सचिन सर
अयो क्या ले हाँ चल मैं बाद में करूँगा तेरे साथ। ओवरऑल लाइक करना सर, ये उस पे फोकस करना है।
बेटा जितने भी बच्चे हैं वॉलेंटियर्स के अलावा बाकी सब जा सकते हैं फिलहाल। यू कैन लीव, ठीक है। कल आ जाना सुबह 10 बजे। ओनली वॉलेंटियर्स कैन स्टे, क्योंकि आपका हॉस्टल का लंच वंच का भी टाइम हो रहा है सब बेटा, और डिस्टर्ब हो जाएगा। कल आ जाना, ठीक है, जल्दी। थैंक यू, यू लर्न अ लॉट। ये आपके सिलेबस में है जो सर ने पढ़ाया था, पढ़ेंगे, दोबारा पढ़ेंगे, लेकिन सर ने बहुत डिटेल में बताया, इतना सिलेबस में नहीं है। चलो जल्दी जल्दी बेटा। ओनली वॉलंटियर्स बी हियर। आप लोग आगे को आ जाइए, वॉलंटियर्स वगैरह सब, टीचर्स, पार्टिसिपेंट्स सब आगे आ जाइए। कल 10 बजे जिनको इंटरेस्टेड हो आ जाना बेटा। टीचर्स बैठ जाएंगे, आगे आ जाइए। हाँ वॉलंटियर्स बैठे रहे जहाँ बैठे हैं, बस थोड़ा आगे को जाइए।
जो एसी वहाँ से एसी आ रहा है, उधर बैठ जाओ, उधर हो।
जल्दी बेटा, सेशन है सबका। आगे को आ जाओ बेटा, आप लोग आगे आ जाओ, पीछे मत बेटा, आगे देखिए, ठीक है, कैरी ऑन।
बेटा इधर आ जाओ। अंसारी सर आप आगे आ जाओ, बच्चे यहाँ आ जाएंगे। अच्छा ठीक, बैठ जाओ बच्चे, हाँ।
Good afternoon, sir. A very warm welcome you. We hope you are doing well. Sir, may I request you to kindly confirm if you can hear us clearly? Sir, are we audible to you? Hello? Okay, sir. Thank you so much, sir. We are delighted to have you with us today. It is truly an honor and a privilege to welcome you virtually to ICRIST-2026, organized by Meerut Institute of Technology, Meerut. With your kind permission, sir, I would now like to introduce you to our audience. It is now time to our invited online expert talk. And it is my great privilege to welcome our distinguished researcher who has made remarkable contribution to the field of telecommunications and quantum communication. We are honored to have you with us, Dr. Satendra Kumar Mishra, sir, Senior Researcher at the Center of Communication and Technical Catalonia, CTTC, Barcelona, Spain. His research focuses on quantum communication, free space optical systems, and satellite-based quantum and classical communication links. He has authored more than 140 peer-reviewed research publications, received over 3,900 citations, has an H index of 33, and has been recognized among the world's top 2% scientists for his outstanding research contributions. Sir, your remarkable achievements and pioneering research continue to inspire the global significant community. We are truly honored to have you with us today. May I request our esteemed speaker, Dr. Satendra Kumar Mishra, sir, to kindly deliver his expert talk. Please join me in extending a warm virtual welcome to him with a big round of applause.
So, yes, sir. Next slide. Next slide. Yes, sir. Yes, sir. Yeah, thank you very much. Yes, sir. My name is Commissioner. I'm working in Sector for Technology Catalonia. This is the government system of Spain. And currently my research is for communication and sensing. I am the head of the quantum network multi-domain research line here. And first I would like to we are in Barcelona technical area, and we are seeking to might be also aware of ICF and CDPC. Both are the regional government institute, and our aim is our research center aim is to focus on the different research area, and we are more focused on the application in the industrial prospect as compared to ICF. And you can see it like this is we are located near the sea. So we are non-profit organization. We are self-funded and with a competitive research grant, and we are more focused on the industrial projects, and we are a part of the General Catalonia. So CTPC non-profit center for public initiative with a high degree of self-financing open the participation of other public and private bodies as well as to partnership with the industrial and business sector. Mission is to excellence flagship center that serves as a bridge between academia and industry, and a center that influences part of communication technology system network and geomatics. So our research unit, we have the 9 research units, and I am the part of the space and business communication system. we are more focused on space interface communication and subsystem, space network resource control and management, and space technology scaling terrestrial system applications. So now, as I mentioned that my more research is more focused on here satellite as the point of communication, and in my presentation I will now also try to show some of the research which I have not performed here but before. So this is more related to different devices and the sensing system. So first, I would like to start what I have started here. I have been developing the quantum distribution, and here we are first time developing the high dimensional memory system. And for that, we started to study about the orbital angular momentum. But before, like for the space communication, promises unparalleled security efficiency for data transmission by leveraging quantum mechanics. However, for the space communication, there's different type of challenges. And one of the challenges when we are transmitting the data, what is the photon loss, what is the signal attenuation, and need to for robust error correction. There is another technique, like now people are like, whole of the world is talking about artificial intelligence and machine learning, and this is really remarkable. They are playing a remarkable role for the modifying and simplifying the system. The I will show you one example how I have used the artificial intelligence with my student, and we are trying to simplify the challenge of the hardware, and that can be really very useful for the developing the new type of device. So we are more developing the hardware perspective where we are using the AI, and how we don't need to develop the more hardware, and can we use the AI to implement our existing hardware and can we simplify the system or not. So I will show you one example. But before that, if I try to see when we are talking about the space communication, like the photons loss and signal attenuation, error correction, and quantum computing efficiency. If you can see the quantum, there is no quantum Q distribution setup is still standardized. Standardized that there is no standardization we have been up to now. Up to now has been done. But people have to follow we also follow the European Space Agency guideline, and we currently working on that. But there's another problem in the global, how we can connect with the global UK network, and the main problem is radiation. So still the research in this area, a lot of research needs to be done, and people are working in a different perspective. So if you think about the quantum correction and noise reduction, quantum signal are extremely sensitive attenuated and noise which can distort the information being transmitted. When we are talking about the photon communication, we are talking about minus 78 dB power. And if you can see the normal communication, the noise level you can get very easily minus 40. So think about that. We are communicating the data in the case of the noise level, and that can be also challenge. So when we are talking about the error consent and not noise rejection, we think about it, how to detect the data, and that can be still a challenge about it. And this also focuses on recovering the lost and corrupted quantum information due to noise error. Noise include this noise can be thermal noise, dark noise, environmental interference that can be trapped. In the case of the satellite, most of the environmental effect is the sunlight. That's why till now there is no quantum communication from the satellite has been done in the day. So if people are talking about the daylight communication in the quantum, that can be not visible. So we are currently working with Thales Alenia Space, and we are launching the geostationary satellite, and we are doing the measurement currently with the day in the night. So the environmental interference can be also affect the quantum signal. So that is a very challenging effect, and we are working on that. So another thing is the photon loss and signal attenuation. Then if you can see the satellite communication, people are talking about the DHCP and DD84 protocol. Since in this case, the data transmission is the polarization indicating. But if you are going to think about the classical continuous variable utility system, there is a problem. Since continuous variable utility system nothing but an advanced level of the normal optical communication. But when you are transmitting the data, this CP2 is very good in the fiber. But when you are transmitting the data from satellite to ground, the problem is the losses. And that losses we know the quantum signal are very low power, and if there is a loss, we have to be we need to develop a very high efficiency detector, and that this is another challenge there. Since the detector, what we have the single NOR single photon detector is still there to efficiency not more than 50%. So how we are going to detect? Either we have to either we have to be develop a detector and other adaptive system to recover the data. Either we have to be think about how to transmit the data. We can design a quantum computing system. So in this case, in this paradox, there's a different type of Qtadi system has been developed. So one is the CP one is the DB Qtadi, and another is the Tangle Qtadi system. So when people are start to talk about the CD Qtadi that is good for the fibers, this fiber is more stable and we don't the losses is not there. But when we are going to think about the satellite communication and the turbulence, the CB2K is not a very good choice. Then people will start to think about the individual carry, and then they have followed the BBS protocol. And that is the currently all the European all the world is calling for the satellite communication, and we have also our test communication work, which we have been developed here, and which is working. So now that, but when we are talking about the qubit, then we have to come to think about what is the efficiency and how it's working. It's still the qubit protocol need to high efficiency and secure the next part adoption challenging into maximizing the key rate instead the overspend of the key rate. So still the key rate is not more than kilobyte and megabyte, and then think about that, how we are far away about that. So still we are working on this challenge, how to improve the quantum efficiency, and definitely this is one of the challenges. Total qubit efficiency mapping that quantify the same information conveyed by single qubit during a qubit protocol. So another thing is that when we if you can see that people are most of the time talking about geostationary satellites. The good thing is that for the geostationary satellite synchronization is the challenge. But now European Space Agency and other people are thinking about EU satellite. And EU satellite is the problem is the synchronization, not flying back. And also since this in the quantum the signal is very low, the power is very low. The problem is the how to synchronize the system. And this is the challenge. And another challenge when you have the turbulence, your signal is moving, very wondering how you are going to couple it up right with the things. And if you are not synchronized, even the fiber is coupling, you will not able to see it. Some of the problem when I do my lab test, I have to struggle 20 days for the synchronization, and later I realized that my system, my everything is good, but the synchronization is. So think about that. If I am working for 100 meters in my lab and I have the problem with the synchronization, when we are talking about the supply 500 kilometers, how big is the challenge? And the Thales and Aerospace, we are developing a new type of bots in our time controller so we can solve this problem. So when we are talking about the global computing network, then we have to think about the video satellite, and this is the creating a new type of paradigm challenge and people are working. Since still the problem is video satellite, the optical communication, which have the high power and high data rate. So think about it. When we are going to think about the QKD system, quantum satellite, and it's a problem. Still need to address like and people scientists are working on this. But in this case, when we are talking about the I say quantum distribution, you know we need a transmitter and receiver, that is the Alice and Bob. So we are sending the data, and we can send it. We have a different type of protocol, but I am more interested in the satellite communication. So we are following the VDX protocol and VDX protocol. Our research group, we are developing the oil-based QKD system for us. But oil-based QKD system has itself a lot of challenges, and we are trying to solve some of the challenges. My student, I told you the simulation, and now we are validating with that study. But if we can solve this, we can solve a lot of problems in the QKD system. That's why my I am thinking why you have to use the OMQT system. OMQT system gives a lot of leverage, like higher information capacity. Let's suppose that if I want to signal, if I want to transmit the data from a normal communication system, so we need to transmit the data with a single level. And if we want to transmit another data, we need to another level. And then we have a lot of devices, we have a lot of complexity that can create a lot of problems. And also, if the webness person is very near the top, in the case of the OMQT system creating a spatial mode and a spatial distribution, so we can include it in a spatial with the same devices, same wavelength, and that can give that a high data capacity with the low cost and enhance resistance. And also, OMQT is very good. I can say the very first challenge is the turbulence in the atmosphere, and OMQT is like I can say we observe that in a turbulence distance. So that can give a very good advantage when we are communicating the data in the central. We have been done some of the calculation, but when we are transmitting the data, the problem is that what is the linear scenario in the I can say in the copy and pen and simulation, you can do whatever. I can transmit 1,000 of the OS, but that is really people in the world of art. We have the exact devices for art. I have seen people are calculating and say, okay, we transmit the 900 OM mode, or 1,000 OM mode, or 1,200 OM mode, but that is the really, you can publish the paper. But can we transmit the linear data? So then we have to think about that. What is the aperture size of transmitter and receiver? And you can see, we have done a calculation and we can see the aperture size for OM of order 2, 3, or 4 is still visible according to the like a legal system, what is available in our optical communication. If you are going to more and more, since the OM would have the divergence nature, then it is very difficult to we can design and we can receive the signal. So now I am going to talk about a simple example where we have to the OM mode and we try to solve the hardware problem, and we are in the process of completion, and how we are thinking like artificial intelligence can solve the problem of the hardware. Since when we are thinking about the hardware, a lot of money and a lot of manpower, and you never know what is the then AI can solve this problem. This is the software we can implement in the device and we can see how it is performance. So my answer is that we have been using the AI and we have solved some problem about that. Now, like what I try to say, orbital angular momentum being a light carrying orbital momentum is what type of structure light, where the field distribution of the light is kind of. So you can see there is a different type of spatial mode, and we can say L1, L2, and what I try to say, when we increasing the mode order, the beam size is increased, and when it is propagating in the space, that it is inherent property of the light. So, OM challenges in OM advantage, OM communication enable high spectral intensity, spatial mode multiplexing, while simultaneously enhancing the physical layers, including the space optical. Practical implementation of OM communication is limited by beam light. Since the beam is divert, and you don't have the like receiver of aperture, you can see the signal. And you can see at the center there is no power. Either you can see no power. So up to 5 kilometers the power is low and the beam is very divert, you can't see it. So then this is the one of the challenge. And where high order modes is straight radially charging the significantly loss outside the receiver. And by atmospheric turbulence, which introduce phase distortion, simulation, and intermodal targeting rated demultiplexing. So then what we can do? Can we use this spatial light model? Can we think about that? How we can use the OM multiplexing and we can transmit the data. Is it possible? So
Like when we are talking about the QKD system or road system, people won't think about the receivers. So we work a lot on the receiver and optic optics. They design the receiver. So what I am thinking, can we do something in the transmitter side? We have tried to do intelligent science. What we have, if think about that, when we are sending the data in the normal, we have the gas theory. But the problem is our when we are going to it. So what we are trying to do, we try to select selective OM mode and we do the superposition. And when we do the superposition, you can see the beam is normally more like a gas beam. And that's good. Since we are sending the signal, and now at the center, we don't have the problem about the donor state or similarity. So we have the power and we can receive the signal. And here you can see how we are selecting the superposition of the wave. So suppose we have intelligently designed our transmitter for the selection of wave mode, for the superposition of selection of wave mode, and we transmit the data. And what we have, we are getting the very good result. So, core idea, use the coaxial orientation. Select modal combination, maximum central orientation. What happened into aperture coupling efficiency since it is said that the aperture receiver aperture can receive the more signal. Reduce divergence, reduce transfer losses. If you have the big, it's very big. I mean, if you don't consider on the aperture creates this work can get translated and that can create a divergence. Think about it. Your signal is going and you have the beam, at the center, when the beam is coming, the divergence will start. So that will also create, if your signal is not more than enough for the aperture size, you can't see any type of translated induced loss and no additional optical fiber. And that is another advantage. Since what we are thinking, one to transmit this data, we need a very big aperture, we need a very big hardware. But using the artificial intelligence, using the selection of more than people, we don't need like a lot of hardware. So now, but the thing this is not the case. We also think that to improve our signal to the using the AI. So here my student developed a trainable AI. We have the fixed so we send the signal and it improves the signal and after that this fixed AI you can see we have the different type of phase mask and we are able to detect the and that is going to be a game changer. So you can see we are designing our system in a way where we can transmit the OM model, selective OM model. We can receive with the existing system. We don't need any new hardware, we don't need anything. We are going to use the same system, whatever the new by the different type of OGS system. And this is the final estimate marks. This is something like about the fund, space communication. Now I am talking about a little bit about my old work and what I have been done with the integrated optics and sensor. So here we are going to, this is some of the part of the work which I have been done by doing my PhD and one of some of the postdoc and some of the work. So I have started my journey with the PhD with the work with the surface quality with the sensor where I work with Institute of Technology under the guidance of Professor and after there I more work on the fiber-based system and then I moved the Hong Kong where we have developed the polymer based guide. First time we have developed the polymer based guide sensor about the surface plastic. Then further I have been working with the US where I have been working with independent communication fiber using SMT metastructure. And I also started the communication with the OEM mode in optical fiber, which I will speak to the concluding my final presentation, where I have been OEM mode and the OEM mode and optical communication. So So when we are talking about optical fiber can be used as fiber sensing in fiber imaging, surgery, medical application, electrical space application, and many more. Not many more. So you can see optical fiber can be used for a different type of application, depending on the way how we are designing, how we are implementing the system, and we can we already this type of devices already in the market. So. But in the case of my case, I have been used surface plug as a sensor. This can increase the surface sensitivity. But before that, what is the optical sensor? Optical sensor. When we are talking about optical sensor, we are giving the input signal and we are receiving the output signal, and we have some external propagation. So sending the input signal with the waveguide or fiber, and with the external participation, what we are getting the output signal, we can characterize in the terms of the either change in the intensity, change in the phase, change in the polarization, and change in the and this type of parameter characterize your sensor how the external perturbation has been affected. And in case in my case, I won't work on the wavelength change, but and then this type of optical sensor have their own limitation about the sensitivity and detection accuracy. So how we can enhance this type of optical sensor performance? So we have been using the surface plasma technique where surface plasma at the point of time is oscillation at a metal magnetic phase and surface plasma and shift only for the TM right line. And this is the one of the things. And here in the surface plasma can be exact when the phase matching condition happen and we have to follow the boundary condition. So after phase matching condition, what the conclusion is that you should have the two medium. One medium should be have the refractive index lower and the real part is lower, negative, another is the positive. And this means that for the excitation of surface plasma, we need a metal dielectric. Only the dielectric constant can be negated. So this is the conclusion. This is the one of the like the main point of the excitation of the surface. Then how we can excite the surface? When we go to the literature, a lot of type of calculation has been discussed about the excitation. The most popular configuration is the crystal. This crystal configuration, usually we use the high dielectric film and deposited the metal film at the one place of the we have the sensing medium, we second the line, after that we have here we have the laser and we have the detector, and after the detection we have see. But the question is that can we excite the surface plasma with a direct light? The answer is no. And why do we need a high direct? When you can see the dispersion curve, you can find that the weight vector for the direct light and weight vector for the surface plasma, nothing is affected. And surface plasma is just condition. That's satisfied. So we have to do the and for that we need a special configuration. Here we know the kind of it means that we have to be doing our paper, our like wave vector, and we can see this is the wave vector. Our surface. And you can see our wave vector of the incident line and wave vector of the central plasma. Here is the centimeter and that can confirm the surface temperature condition. A surface plasma phenomenon can be happened. So this is the reason why the direct light cannot excite the surface plasma and we need a special type of configuration by excitation. Now, you can see this is some example, and in my case, I have to work on a chemical environment setup, and then I have to work on a gases. The funny thing is that for that, you can see most of the setup is same, only we have to change our sensor. And the sensor depends on our requirement and so on is transfer. And in this case, we use the like a tube for the putting the light and sensor in here. We use the gas chamber, but the remaining setup is the source and detector. So we have been design our sensor either according to our requirement, what are our aim or what we want to test. And but the testing setup, our test bit are the same. But only for the gas sensor we need to use distance. So we need to jump against them in case of the like chemical and fire sensor.
Sorry to interrupt the team. Actually, there is some delay in the stream, so can you please wait for a minute and restart again?
Okay.
Yeah, just wait for 1 minute and let me restart. I will inform you.
Okay.
सर